This lecture is brought to you by CNCB Academy of Science and Technology. Visit us at cncbacademy.com.
The title of the lecture is Nobel Prize 2023 Physics, The World of Attosecond Physics. I am Devasis Sanyal and I am an associate professor in the Department of Physics. So in this lecture we are going to deal with the physics of attosecond science, the generation of attosecond pulse, where we come across attosecond timescale and an example. Let's get started. So in 2023, 3 scientists were awarded the Nobel Prize in Physics. Pierre Augustini from Ohio State University, USA, and Anne L. Huvelier from London University, Sweden, and Fredrik Cross from Max Planck Institute, Germany. So we go to the next slide. So attosecond physics is about nonlinear optics. Before we get into the topic, we will briefly discuss the electromagnetic spectrum because it's required for our work. So what we see is the electromagnetic spectrum. On the left hand side we have the very energetic gamma rays, and on the right hand side we have the radio waves. Our region of interest lies in this region, extreme ultraviolet to soft X-rays. This is where we will be interested in, and why so we will find out in this lecture. We will be working with wavelength of around, say, between 10 angstrom to 200-300 angstrom. This is the region we are going to work with. So ultraviolet, anything beyond 10 angstrom will be ultraviolet. Ultraviolet has a very broad range, but we will be working from, say, around from 10 to 200-300 angstrom. So we go to the next slide. So what we have here is the fundamental relation in electromagnetic radiation, which connects the wavelength to the time period of oscillation for a sinusoidal wave. So this is lambda and this is time. So lambda is equal to Ct, where c is the velocity of light. We'll go to the next slide. So now we are going to have a look at the ultra-fast timescales. So when I said attosecond, so what is attosecond? So before we come to what is attosecond, we'll try to understand the different timescales that we deal in physics. So what we have something called picosecond. So 1 picosecond is 10 to the power minus 12 seconds. There is also femtosecond. Femtosecond is 10 to the power 15 seconds, is 1 femtosecond. And then we have attosecond. So this is our interest. So attosecond is 10 to the power minus 18 seconds. This is attosecond. And then we have femtosecond. Femtosecond is 10 to the power minus 21 seconds. So why we are interested in attosecond? So first of all these time scales, they probe particular dynamics in molecule. We'll come to that, what kind of dynamics each time scale probes. So 10 to the power minus 12 seconds probes a particular kind of dynamics, 10 to the power minus 15 probes a particular kind of dynamics, 10 to the minus 18 seconds or attosecond region probes a particular kind of dynamics, and femtosecond probes another kind of dynamics. So why is attosecond important? So you can see this is an extremely small time scale. So why we need this? So where do we come across this kind of time scale? We go to the next slide. This kind of time scale, when we say of attosecond, you come across this time scale when we are considering the motion of electrons in atoms. Okay, so when I say attosecond, it doesn't mean 1 attosecond, 2 attosecond, 3 attosecond. I mean 100 attosecond, 200 attosecond, 300 attosecond, like that. Now, what is the plan of this lecture? The plan of this lecture is we are going to define what is pulse, what is pulse train, then we will briefly review what is Fourier transform, Fourier series, because all these things are necessary to understand attosecond pulse. Then we are going to understand how do we generate attosecond pulse. Then we are going to connect attosecond to electronic motion, and finally we are going to deal with an example of attosecond time scale. Particularly, we will be dealing with an example of photoemission. We go to the next slide. So, attosecond spectroscopy is about, loosely speaking, filming the motion of electrons. So when you come to our regular camera, there is something called shutter speed. So what you can see that if a person is running, and if the shutter speed means the shutter opens and closes in 1 second, then you can, when you photograph the person, you can see that it comes out hazy. So if you increase the shutter speed, things improve a little, but not that much. So you can see as you go to the right, you are increasing the shutter speed, and as you increase the shutter speed, you can see that you can clearly picture the person running. So my attosecond pulse is something like, loosely speaking, definitely it's not like a shutter, but my attosecond pulse is like a shutter of the camera. So when you are trying to measure a motion which happens in a time scale of 100 or 200 attoseconds, we need a pulse which is of that order. We go to the next slide. So now we go to the Fourier transform. So what is Fourier transform? So we have, this is my signal ft. So we have a signal ft, and we want to find out what are the frequency components it is having and in what strength. So for that we have to do a Fourier transform. So this is a typical Fourier transform relation, and on the left hand side we get the amplitude corresponding to the frequency omega. So if you want to calculate the intensity corresponding to omega, we just have to do G into G star, that is this complex conjugate, and we will get G star, and we will get the intensity corresponding to omega. So we will know how much energy is contained in the frequency omega. This is the concept of Fourier transform. We go to the next slide. Transform of e to the power I omega 0 t. So we will take the Fourier transform of this. The complex part corresponds to the sine wave. So if you take the Fourier transform of this, what we get is a delta function. So this is a delta function, that is, it has value only at a particular value of omega. So this is the omega axis and this is my amplitude axis. So at all other portions this amplitude is 0, only at omega is equal to omega naught there is contribution. So this has frequency component omega naught, that's it, and there is no other frequency component. We go to the next slide. So that was a simple Fourier transform of e to the power I omega 0 t, and we obtained that there is only one component omega naught in the Fourier transform. So instead of that we can take a rectangular pulse. So this is this is my ft. Okay, so this is my ft now, a rectangular pulse, so which switches on at minus tau by 2 and switches off at tau by 2, and it is 0 on the right hand side and 0 on the left hand side. So if you take a so this is like, you can say this is a pulse and it has a width tau. So this is like this is a rectangular pulse and this is a width tau. So this is a rectangular pulse, you can say this has a width tau. This is a width tau. And I can take a Fourier transform of this rectangular pulse. And if you take if I take a Fourier transform, what do we get? We'll see it in the next slide. This is what we get when we take a Fourier transform. So this is, so y-axis is the amplitude and the x-axis is the frequency. So you can see that there is a maximum contribution at omega is equal to 0, where the amplitude is maximum, and as I go to the right or left, the amplitude keeps on decreasing. One thing you can see from here, that if I want my tau to be very small, that if I want the pulse to be a very short width in the time domain, if this tau has to be small, this tau has to be small, so that means this width increases. So this is what we call the bandwidth. The bandwidth increases. So more and more frequencies become relevant. And if I increase tau, that is my pulse width is increased, then what happens is that this bandwidth decreases. So lesser and lesser frequencies become important. So this is how it goes. Now, one thing about this is that this pulse is centered about omega is equal to 0, and we know that omega is equal to 0 does not propagate. You know, it is sine omega t. Like sine omega t means omega is 0, that means, or cos omega t, that means the time part is suppressed. That is, such a pulse does not propagate, and if the pulse does not propagate, that is not acceptable to us. So this kind of rectangular pulse is not relevant in our case. So what do we need? That we will see in the next slide. So this is the kind of pulse we will be working with. So this pulse, we can say it has some width. We will say that width is, this is a pulse whose width is, say, tau. We will be working with such pulse. And why we just say that we will be working with such pulse, we will see. So what we want to see is when do we, what is the constraint on this width of the pulse tau? What is the constraint? Can it be made arbitrarily small, or arbitrarily big? Is there a constraint? Of course there is a constraint. Tau cannot be made arbitrarily small. And what is the constraint? Let's see. So next slide. Now if you take a Fourier transform of the previous ft, that is the pulse that we showed, we'll get a typical behavior like this. It's like a bell-shaped curve, and it will have a peak at a certain frequency omega naught. It will have a peak at a certain frequency omega naught, and if you go to the right or the left, the curve, the intensity will come down. So on the y-axis we have plotted intensity. The intensity will come down. So the intensity is maximum at omega naught, and this curve has a width. The width goes as 1 by tau. That is, if I want to, what I want is a very small width. I want the pulse to be a very small width. So tau is small. If tau has to be small, then this width has to be large, right? So if I keep on decreasing tau, then what happens is that my width has to be large. So my width will be like this. So here it is like this, and so the width will say it has to, like, if I decrease tau, then my width will become like this. That is, more and more frequencies become relevant. That is, the bandwidth is increasing. And another important takeaway is that if the central, so this is my central frequency omega naught. So if the corresponding time period for central frequency is my capital T, then the tau has to be always greater than equal to T. It can never be made smaller than capital T. So capital T, so what is the capital T? So capital T is the time period of oscillation of the central frequency. And what happens is, in a pulse, like I showed in the previous slide, there is a modulation in time. So the amplitude decreases on both sides, like I showed before. So a pulse has to be oscillatory. So in order to be oscillatory, at least there should be one cycle. One cycle means there has to be at least one time period. And if there has to be one time period, that means your tau cannot be made smaller than that one time period. So tau has to be greater than equal to time period. And how much greater it will be compared to this time period, that will depend on whether how much of the other frequencies are there. Like, apart from omega naught, what are the other frequencies, and how much of those frequencies are contained in the pulse. That will determine the width of the pulse. So if I want my pulse to be really very short, always tending to capital T, then what I have to do is that I have to increase, so this bandwidth has to really increase. So I have to include more and more frequencies so that this one really becomes wide. So the takeaway is that the width of the pulse cannot be shorter than the time period of the central frequency. So this we should remember. So when we want a very short pulse, remember our time period has to be also very short, is it not? So if I want, we'll come to that. So that means that suppose I want say suppose I want my tau to be, say I want my tau to be of the order of 100 attosecond. Then this implies that the wavelength corresponding to the central frequency has to be, this lambda has to be around 300 angstrom. Or less. It cannot be more than 300 angstrom. It can be 300 angstrom, it can be less than 300 angstrom, but it cannot be more than 300 angstrom. That's why I was telling that we'll be working in the extreme ultraviolet or soft X-ray region. Or if I want my if the central frequency is, say if the central frequency is, see here, omega naught, if the central frequency has a wavelength corresponds to say 100 angstrom, extremely very hard ultraviolet, so this is 100 angstrom, then my tau will be greater than say 40, that's really very short, 40 attosecond, round about that. So you can make tau as low as 40 attosecond. So that depends on whether you make it 40 attoseconds or 60 or 70 attoseconds, depend on how much the other frequencies are also present. So this is the idea. So what is the takeaway? So final takeaway we'll see in the next slide. So requirement for attosecond pulses, broad frequency spectrum, and the central frequency should be in XUV or soft X-ray region. So this is the important thing. Once you remember this, then things will be easier to understand. So till now we are talking of a single pulse. We dealt with a rectangular pulse, but that was rejected because if you take the Fourier transform of rectangular pulse, it has its Fourier transform is centered about omega is equal to 0, and omega is equal to 0 wave does not propagate. And then we discussed the kind of pulse we would require, and we also saw the condition for the pulse to be in the attosecond region. So that the width of the pulse depends on the central frequency of the pulse as well as how much the other frequencies are present in the pulse. Now we will go to the concept of Fourier series. So for that, what we see here is this is a rectangular pulse. So here what we have is the pulse is on between this time and then off. This is the off. This is the off. Again the pulse is on and again pulse is off, and it continues like this. and this is the time period of t is equal to 2. So we go to the next slide. So when do we do Fourier series? So the previous slide was an example of a periodic motion or periodic pulse. So Fourier series can be applied when the function of time is a periodic function, that is, it has a period, so it has a period t. That's when we can apply Fourier series. And what else? When we do the Fourier series will contain, so will be written as some constant term plus summation over some an cos omega n t plus summation over some bn cos omega n t. So what are these omega n's? These omega n's are integral multiples of omega naught. And what is omega naught? Omega naught is the fundamental frequency of the periodicity, or it can is related to the time period as t. In the previous case, the time period was t is equal to 2. So this is called the omega naught is called the first harmonic. So in general, these omegas are integral multiples of omega naught. So we can have n is equal to 1 corresponds to first harmonic, n is equal to 2 corresponds to second harmonic, n is equal to 3 corresponds to third harmonic, and so on and so forth. So we will require the concept of harmonic later on. Go to the next slide. So here we have a square wave. So you can see, so what we have is, this is a wave, so this is a pulse, it's on, then it's off for a certain time, it's off, and then it's on, but its sign is reversed, and again it's off for a certain time, and then it switches on again, but again this sign is reversed. Okay, so this is a time period. So this is the time period of the pulse, this is shown here. And what we see here, that, so what I want to say through this example is that it's not necessary that all the harmonics will be present. Like n is equal to 1, 2, 3, 4, 5, 6, 7, 8, all the harmonics may not be present. Some harmonics may be absent depending on the type of pulse we are dealing with. So this is just an example. So we'll go to the next slide and see what I want to say. So in the previous example, what we saw was this, f of minus t was minus of ft. This symmetry was there, and this symmetry was also there. ft plus t by 2 was equal to minus ft. You can see, so f, this is, and if I transport it by half the time period, then what we get is a negative sign. So that symmetry is there. And ft, so this is an odd function, this ft is an odd function, that is very obvious from here. So if that is the case, then what we have, this ft can be written as bn sine omega n t, where now only the odd harmonics are present. This is just an example that all harmonics may not be present, only odd harmonics are present in this case, where n is equal to 1, 3, etc. And omega n is equal to n omega naught, where omega naught is the basic frequency, or if t is the time period, then omega naught is equal to 2 pi by t. And what we will see in this case, if you do the calculation, bn goes as 1 by n. So as n increases, the amplitude of the higher harmonics decreases as a power law. So there is no, what we will say this, actually there is no scale. This is no scale involved. And that's why, since no scale is involved, if you take a Fourier transform of a single pulse, we will find it that it is centered at omega is equal to 0. So no scale means the central frequency is omega is equal to 0. There is no scale involved here, so it's just going as power law 1 by n. That means no scale, and so if you just take a isolated pulse and take its Fourier transform, we will find it is centered at omega is equal to 0. So that's of no use. So that kind of pulse we will not be working with. So we will go to the next slide. At the beginning of the lecture, I had talked about nonlinear optics. So in this slide, we are going to discuss a phenomena that is related to nonlinear optics, and it is one of the first discovered phenomena in nonlinear optics. This is called second harmonic generation or frequency doubling. So what happens is that when laser light is passed through certain crystals, due to realignment of the crystal, what you get virtual states like this, and what happens is that the laser photon is absorbed first to this virtual state and then to the other virtual state. So another photon omega is absorbed, and from this virtual state the crystal relaxes back to its ground state by emitting a photon which is 2 omega. So what we have, if you consider the intensity versus the omega spectrum, so there will be emission at omega, at frequency omega, as well as there will be some emission at twice omega also. This is called the second harmonic generation signal. So this also you will get from the crystal, or this is also called frequency doubling. What happens in Attosecond physics is that not only second harmonic is not about the second harmonic generation, many higher order harmonics are generated, and that leads us to the physics of attosecond pulses. We will see it soon. Now go to the next slide. So first we are going to study generation of attosecond pulses in free electron lasers. So this is free electron laser. This is one of the advanced techniques for generating attosecond pulse. And then we have what is called generation of higher harmonics. This also we will discuss. So first we will go to the generation of attosecond pulses using free electrons. So how does it happen? Let's see. So in free electron laser, what happens? First we need an accelerator. So what the accelerator will do is that it will accelerate the electron to relativistic speed. That is, the electron will travel almost at the speed of light. Then this electron is injected into a system containing magnets. So here you have magnets with opposite. So here you have a magnet, and here you have magnet with opposite polarity. And here you have magnet with opposite polarity. So you have an array of magnets, and so suppose the magnets are aligned vertically, and this electron is injected into the system in a plane that is perpendicular to the perpendicular to the magnetic field produced by the magnets, and when it enters when it enters the space between the magnets, because of Lorentz force, it now curves. So you can see, so what will happen is like this. So electron will enter, and then because of magnetic field it will curve, and as soon as it enters the magnetic field of the other magnet, it will again curve, because that magnetic field has opposite direction, and then it will reach the magnetic field of the other magnet, and which is again oppositely directed, so it will again curve. So it will go in a zigzag path in that plane. So what happens is, because of this acceleration, so whenever it's like changing direction, is accelerating. So the acceleration is maximum when it's changing direction. This acceleration will, due to this acceleration, it will give off electromagnetic radiation. We know that if a charged particle is traveling with an acceleration a, then the total power in the form of the charged particle emits in the form of electromagnetic radiation is proportional to a square, that is acceleration square, and it is proportional to gamma 6. Gamma is in relativistic mechanics, gamma is root 1 minus b square by c square. So for relativistic electron, gamma is very high. So this intense power means the emitted photon has very high energy. So almost in the X-ray region. And now what? Here I have talked about only a single electron coming and then going zigzag. But I need attosecond pulse. So for obtaining attosecond pulse, I need a bunch of electrons. So the trick is, a bunch of electrons is injected into the space such that temporarily, that is in time, they are very close, that is they are bunched together, but even though they have relativistic speed, their velocity is varying. So as a result of that, these bunch of electrons will emit different frequencies. So we will have a central frequency which is very high, and we have other frequencies also to the right and left of this central frequency. So this creates the perfect condition to have attosecond pulse, and that is how attosecond pulse will be generated in this arrangement. So a bunch of electrons going across this array of magnets in a plane will give rise to what we call attosecond pulse. This kind of arrangement is there in Stanford University because they have accelerator which is called the SLAC. Stanford University Linear Accelerator Center, SLAC. So there they employ this kind of method to generate attosecond pulse. We'll go to the next slide. In the next slide, what we are going to use is it called titanium sapphire laser to produce higher order harmonics. So to generate higher order harmonics, we need a titanium sapphire laser. So this is a solid state pulse laser. So this is this sapphire is doped with titanium, and titanium is the lazing material, and sapphire is a very good conductor of heat. And the central wavelength, that is this titanium sapphire laser, works very well at this frequency or this wavelength, 800 nanometers. 800 nanometers means 2.6 femtosecond. So you can see that this titanium, so this is a pulse laser, so it produces pulses, but since the central wavelength is 800 nanometers, or if you convert it to time period is 2.6 femtosecond, you cannot have attosecond pulse using this laser. But we will generate attosecond pulse. So this laser does not directly produce attosecond pulse, but due to nonlinear effect, we will see that this laser can be used to generate attosecond pulse. So from this laser, what we get, you can have pulse width of around, say, 10 to 100 femtosecond. As we see that if your time period is 2.6 femtosecond, your pulse width cannot be less than this. So using various tricks, using this laser, you can have you can have a pulse width of 10 to 100 femtoseconds, but you cannot do better than this. And how to do better than this, we'll see in the next slide. So how do we generate higher order harmonics? So this is this very schematic diagram. So here we have on the left hand side, we have the laser, the pulsed beam that is being generated by the titanium sapphire laser. So it's entering a channel, and in this channel what's happening is a gas stream. The gas typically consists of noble gas, argon or xenon. It is being pumped through in this direction. So this gas is being injected in this direction. So there is a jet in this direction. A laser is acting in this direction. It's coming in this direction, and the output what we get is the XUV pulse stream. So this is what is this. That is how higher order is generated. So you have laser beam. This is a gas stream consisting of, say, argon gas, and when this laser beam interacts with the argon gas, something happens, and on the other side what you have is you have attosecond pulse stream. So you don't have single attosecond pulse, you have a train of attosecond pulse that is coming out of this at the other end. And how does it happen? How do we get attosecond pulse first? From this setup, and we will see that in the next slide. Previous slide, through a spectrometer or grating, this is what we get. So this is the plot of intensity versus the R harmonics. What you can see here, that only the odd harmonics are generated through this process. So you can see this is the first harmonic, omega naught, then we have the third harmonic, 3 omega naught, then we have the fifth harmonic, 5 omega naught, then we have the seventh harmonic, 7 omega. Like this, if we continue, this will be the, say, 33rd harmonic. So this will be 33 omega naught. And we know what is omega naught. So omega naught here corresponds to a wavelength of 8 100 nanometers or 8000 angstrom. So intensity is along the y-axis and frequency is along the x-axis. What is observed initially, there is a drop in intensity with the high harmonics, but this is the most interesting region because this is a plateau region. So what we have is a plateau region. That is, even though the harmonics are increasing, so in this direction harmonics are increasing, the intensity does not change. Intensity remains the same. What we have seen is that with increasing harmonics, the intensity decreases as some power law. But here it does not. Here it is a region where the intensity holds steady. And then after that, the intensity drops sharply. So what we conclude from here is that this graph tells us that in this problem there is a scale in frequency, and that scale is approximately 33 omega naught. And 33 omega naught, what does this scale represent? This scale represents the approximate peak of individual pulses at the output. So output contains a train of pulses, and that is why we have these harmonics, but every individual pulse is centered around 33 omega naught, and this is a very high frequency. 33 omega naught, like if you convert it into wavelength, so that wavelength should be around, I think, must be between 200 and 300 angstrom. So now we are in a region where we can have attosecond pulse, because this corresponds to very high ultraviolet, 200 to 300 angstrom, and that is how we start with infrared pulse and we end up having pulses centered at very high ultraviolet frequencies. So now we will go to the next slide. So here what we have is this one. This is the one. This is the wave that is coming from the titanium sapphire laser. The laser has a very strong field. It is around 10 to the power 14 watt per centimeter square. So this is oscillatory. So here we are considering one cycle. So what happens is that when the wave is at its when the wave is at its peak, what happens is that the electron, the outer electron, gets ionized. So here you can see the electron is in a potential well, and when the wave is at its peak, then what happens is that this potential is distorted and quantum mechanical tunneling happens and the electron escapes. So this electron, say the blue one, escapes and it moves away from the atom. And at the same time, now you can see the infrared. This is the infrared wave. Infrared is changing direction, but here the infrared is changing direction, but the electron does not change direction immediately. It will change direction somewhere later, and finally it will change direction and again fall back into the atom, and the atom will capture it, and all the excess energy will be released as your energy. Say this is maybe 100 electron volts, say. Similarly, an electron which is here is electron which is here. So what it will do? So it will also get ionized, but it has ionized a little later. So it will travel a lesser distance. Okay, because it will be able to attain less maximum velocity, and it will eventually fall into the atom somewhere here. So it will have less kinetic energy when it falls back. So suppose it will so when it falls back, it will emit a photon of say energy 50 electron volts, and another electron. So these are statistical events. So another electron that is here will ionize later or tunnel later, and it will also move away from the atom, and again as the wave changes direction, it will also change direction later on. But for it will happen faster because it was ionized later, so it will not be able to attain a higher velocity, maximum higher velocity. It won't be able to attain a very high velocity, so it will come back soon, and it will be again fall back into the atom, and that way it will also emit the excess energy. But since it has less energy, it will emit say 10 electron volt. So all these things are happening in a very short time scale, and so you can see there's a considerable bandwidth from 100 electron volts to 10 electron volts, and so most of the electrons will be emitted in this 100 electron volts region, which is like very high energy, and that is how we will get. So all this together forms what is called an attosecond pulse. So attosecond pulse will be formed by the electrons that are being emitted in this cycle of the infrared pulse from the laser. And again the same thing will happen here. When the infrared pulse reaches the maximum in the negative direction, then electrons here will be ionized, and again it will be emitted here. So for every half a cycle there will be emission of attosecond pulse, but in the opposite phase, and that is how we get a train of attosecond pulses. So we will go to the next slide now. Why attosecond pulse? Why in electronic motion we come across attosecond timescale? We'll answer this question in the next part of this lecture. So I'm going to end right now. Thank you. This is the second part of the lecture titled Nobel Prize 2023 Physics, the World of Attosecond Physics. And I am Devashish Sanyal from the Department of Physics. In the first part, we discussed about the generation of attosecond pulses and the physics behind the generation of attosecond pulses. So let's get started. We'll start from where we left last time. So why attosecond pulse? So in this second part we are going to discuss how do we come across attosecond timescale in physics. We know that Attosecond timescale is very characteristic of electronic motion in atoms or molecules. And why is that? So for that we have to do a little bit of quantum mechanics. So why attosecond pulse? So first let us construct a state in the coherent superposition of two states. Now, before we talk about superposition of two states, from quantum mechanics we know that if this is my energy wave function, then the energy wave function can be written as a spatial part and the temporal part. So this is the temporal part. So the temporal part gives me the evolution of the energy eigenstate or eigenfunction. And if the particle is the system is in energy eigenstate, then this probability of finding the particle at any position r is given by ue to ue star, and which is independent of time. Now if you go to coherent superposition of states, then this the wave function is now written as a superposition of two energy eigenfunctions. So it's psi e1 and psi e2. So this is the weight factor. It can be complex. C1 is a weight factor which can be complex, and C2 is another weight factor which is complex. So this kind of state can be even construct experimentally. It's not only a theoretical construct. This can be done experimentally. So next what? So if psi e1 is an energy eigenfunction, then you can write psi e1 as I had discussed in the previous slide as e to the power minus I e1 t by h bar into u e1 r and psi e2. Similarly, you can write psi e2. Now we want to construct, or we want to find out the average position of the particle which is in this. So average position of the particle or electron which is in this state. And from quantum mechanics we know the prescription. So average position is psi star r psi dr. This is how we find out the average position. And when we actually find out the average position, we are going to see something very interesting. So for that we have to go to the next slide. Now if you calculate R, it's not very difficult to calculate R average, I mean to say. This is R average. Okay, this is R average. Everything is average in quantum mechanics. So what we are finding out experimentally also R average. So when you calculate R average, in that R average is a real, it has no complex part. So when you calculate R average, we will see in the expression, you will get terms like this one. E to the power I E2 minus E1 T by H cross. This kind of term will not vanish. So what does it tell us? It immediately tells us that there is some kind of oscillatory effect in this expression. You can identify this e to the power I E2 minus E1 T by H cross with some kind of frequency. e to the power I omega t. So this has the dimension of frequency e2 minus e1 by h cross. So I can write omega is equal to e2 minus e1 by h cross. And if I have omega, from that I can calculate time period. So what does it tell us? That the average position for a particle which is constructed in the coherent superposition of psi 1 and psi 2 actually oscillates. And it oscillates with a time period capital T. So the electron cloud, we see the electron cloud will oscillate between two positions. And that the characteristic time of oscillation will be capital T, which is 2 pi by omega. Once we have this concept, we will see what this means in a real situation. So for that we have to go to the next slide. So here we have a real life situation, where we are talking about hydrogen atom. And we know the hydrogen atom, for hydrogen atom there is a 1s state, there is a 2s state. So we are dealing with two energy states, one is 1s and other is 2s. So here we know the energy of 1s state, that is minus 13.6 electron volt, and E2s is minus 3.4 electron volt. So this is the 1s and 2s energy levels of hydrogen atom, and we are going to construct the electron which is in a coherent superposition of these two states. If we do this, then what happens? We'll go to the next slide. This is the wave function of 1s and 2s. 1s and 2s both are spherically symmetric. So it only depends on the position from the center to the point. That is, it depends only on r. So we'll go to the next slide. Now, in the expression that we had, UE1 is U1s and UE2 is U2s. This is trivial. And E1s is 13.6 electron volt minus, and E2 is minus 3.4 electron volt. So you can see, if you do the subtraction, it comes out of the order of 10 electron volt. And this is 10 electron volt. And if you substitute this value in the expression that we had found out for T, you can see that it comes to around 400 attoseconds. So this period of oscillation is 400 attoseconds, or 400 attoseconds means 0.4 femtosecond. That is, to find out this time to find out this time period of oscillation, we need attosecond pulse. So this is one example where we need attosecond pulse to calculate the time period of oscillation. This is not the, so this actually tells us many things, this expression. We don't have only electronic motion in a molecule or atom, we have rotational motion in a molecule. So instead of that, we can deal with rotational coordinates, and when we deal with rotational coordinates, it's very characteristic of rotational energy levels that this energy difference between rotational levels is very less. We found out in our example of electron in atom, in hydrogen atom, it was 10 electron volts. For rotational spectrum, the difference between the various energy levels is of the order of 10 to the power minus 3 to 10 to the power minus 4. And if you plug in this expression in the value, we get T of the order of 10 to the power minus 12 seconds or 1 picosecond. So this is picosecond spectroscopy. Picosecond spectroscopy generally deals with rotational spectrum. It deals with rotational spectrum. So we go, similarly we can have vibrational energy levels, and for vibrational levels we can deal with vibrational coordinates. For vibrational energy levels, the difference between the various energy levels is greater than what we find in rotational energy levels. So here it is 10 to the power minus 1 to 10 to the power minus 2 electron volts. So if you plug in this value in the expression for capital T, what we get is 10 to the power minus 15 seconds or femtosecond. So this is femtosecond spectroscopy is generally about vibrational degrees of freedom. Vibrational degrees of freedom. And then we have electronic energy level. Electronic energy level generally ranges between 1 and 10 electron volt, and if you plug in this typical value, we had shown that it comes to around 10 to the power minus 18 seconds or attosecond. So when we say attosecond, that's why we say with electronic motion. Femtosecond, vibration, picosecond, rotation. And next there is another time scale. When we are in the nucleus, the energy levels of the nucleus, the difference between them is extremely high. This is of the order of, which is order of your 1 keV. And if you plug in this value, what we get is 10 to the power minus 21 seconds or femtosecond. We don't have such pulse yet. Even attosecond pulse is difficult to generate. The attosecond pulse is difficult to generate on a regular basis. Forget about femtosecond. We are very, very far away from femtosecond. But if you are able to generate femtosecond pulse, then you will be able to visualize motion in the nucleus. So in the next slide, we will go to an example where we will use attosecond pulse. So let's go to the next slide. So this slide is titled Attosecond Stopwatch in Photoelectricity. So what we are going to see, so here photoelectric effect is involved, and the substance is nitric oxide. Substance is nitric oxide. So nitric oxide has nitrogen and oxygen, but there are two bonds, and there will be one electron in nitrogen that will be very unstable. So nitric oxide is a free radical, it's unstable. So when this substance is illuminated with light, what happens is this electron associated with the nitrogen comes out early. So this comes out early, and after some time this this electron comes. So first this thing, so there will be two electrons coming out, but first this one will come, then after some time this one will come. So what we are interested in is what is the average time gap between these two electrons. So thing is that the time gap will not be constant, so it is statistical. So what we are interested in the average time gap between these two. And generally, under normal circumstances, the time gap between these two will be typically some 100 to 100 attoseconds. So that's why we have to use an so how are we going to find the time difference between these two? So there's a trick. One is so we'll be using two pulses. One will be the excitation pulse, which is the attosecond pulse, and then there will be the probe pulse. So let's see how it's done. So for that we have to go to the next slide. So here we have an attosecond pulse which is linearly polarized, and so this axis, this you can say is the time axis. This is the time axis. This is the time axis, and this is the intensity axis. So this picture is say at a particular position. So this is my linearly polarized attosecond pulse. So why attosecond pulse? Because we want to only concentrate in the time scale of that phenomena. We don't want to go beyond that time scale, because otherwise, if the attosecond, instead of attosecond pulse we use some pulse which is wider, then other kind of spurious effects may come into the picture, and that will spoil the measurement. So we have to keep it to the attosecond regime, the pulse. So this is my time, and this is a linearly polarized line, and the sample is kept somewhere. So this attosecond pulse goes and hits the sample. Here we are talking of one attosecond pulse. Remember when we had talked about higher harmonic generation, we had a train of attosecond pulses. Let me tell you, it's not, you don't have to always generate a train of attosecond pulses. There are very remarkable methods in which you can create only one attosecond pulse. So you can just create one attosecond pulse and then pass it through the nitric oxide. And so what happens? The electrons will be, so first the nitrogen electron will be emitted, and then after some time the oxygen electron associated with the oxygen will be emitted. And then what happens? Then how do we measure the time difference between them? So always we need a probe. So this has done that. So attosecond pulse has done its job. Okay, it has excited the phenomena that we are interested in. Now we have to take the measurement. So how do we do it? We will go to the next slide. So here we have infrared probe pulse. So infrared probe pulse means that a second pulse has done its job. This is infrared, that is, it is a slow pulse. Remember, if it's attosecond, it will be like high ultraviolet, and infrared means it will be high ultraviolet will be 200, 300 attoseconds, and infrared will be 300 ultraviolet is in terms of wavelength it is 200, 300 angstrom, and When we talk of infrared, it is 8000 angstrom. So what does it do? So what you can see here, again the same thing. So here you can say this is the time axis. So this is at a particular position, say inside the sample of nitric oxide. So this light is circularly polarized. This is circularly polarized. This is circularly, this is circularly polarized. So you can see, so time is increasing in this direction. So here what we see is this is the electric field. So these arrows are electric field. So electric field is rotating like this. As time goes, the electric field is rotating. This is typically circularly polarized light. Here it is rotating in a clockwise sense. Okay. So what happens is, suppose this is the first electron. So this is my first electron. The first electron is somewhere here. So let me just change it. So the first electron is somewhere here. So when it's emitted, it gets a kick. And that kick is the kick it gets from the electric field, which is, say, oriented in this direction. At that moment, the electric field in the circularly polarized light is oriented in this direction. So it gets a kick in this direction. Fine. So it leaves in that direction. And then this electric field is rotating, and at some point of time, this second electron is emitted. And when the second electron is emitted, it gets a kick in some other direction. Right? So when it gets a kick in some other direction, what happens? It moves in that direction. And now the picture is very clear what happens. So for this is, in the next slide, we will go to what is called the Attosecond stopwatch. So Attosecond stopwatch. This is my Attosecond stopwatch. So this is, if you go around it once, so this is the infrared time period. The Attosecond stopwatch can measure time, which is the time period of the infrared probe pulse, right? If it cannot measure any time which is greater than the infrared probe pulse. So this is like the face of the clock, say. So when the first electron is, say, emitted, it gets kick in this direction, right? It gets kick in this direction, so it is detected here. And when the second electron is emitted, it gets kick in this direction, and it is detected here. So what happens is, if you can measure the angle between these two, then you can find out the time taken between these two emissions. That is, what is the time difference between the emissions of these two electrons. How? If this angle is theta, then we know that omega into time is theta. Omega is the frequency of the infrared pulse. Then the time is equal to theta by omega. Omega t is equal to theta, so t is equal to theta by omega. So we have found out the time taken between these two emissions. So I'm going to stop here. I won't go any further. I've left out many topics like if you like once we generate an infrared pulse, we can find out its characteristics like what is the duration of the pulse, what is its profile in space, how does it change with time. All these things can be found out. So those things are more involved, so I have skipped here. This was just to give you a general flavor of attosecond physics, the generation of the attosecond pulse and what you can do with that pulse. So with that, I end here, and so here what? So here we have. So here we have the acknowledgements. You can refer to the lectures by these scientists.